Welcome, everyone. Thanks so much for attending our first webinar in our 2022 webinar series. And today we're really honored to have MIT professor Admir Masic, who's affiliated with the Department of Civil Environmental Engineering here at MIT. And he's going to present to you on the future of more sustainable concrete. And so just to give you a little background on Professor Masic and his work, his research conducted at the Masic Lab at MIT centers on characterizing biomineralized and archaeological structural materials to inspire the design of more durable and sustainable materials today. And the presentation he'll be sharing with us is going to present an overview on a number of the technologies that are in development today that can help cut concrete's environmental footprint. And a number of them are coming right out of his lab here at MIT. And so before we begin, we're going to start in just a few minutes. I just kind of want to outline today's format. So we have all of you guys on mute here, but we encourage you to ask questions via the Q&A panel at the bottom of the screen. And once the presentation is concluded, we'll start posing some questions to Professor Masic, and so he can then answer your questions. And of course, we'll be getting back to you with a recording of the webinar along with Professor Masic's email, so you can feel free to ask him your questions directly after the presentation as well. And so I think without further ado, I'd like to hand the floor to Professor Masic.
Thank you, Andrew, for this kind introduction. And also thank you, CSH Hub, for this opportunity to share some recent developments in my lab around the sustainability of cementitious materials and also around the tools that we use to investigate these materials. So when we talk about Masic Lab, indeed, we talk about looking into inspiration. And we search inspiration from ancient materials as well as biological materials. And we basically use multi-scale characterization tools that include chemomechanical characterization of these, material models with the objective to understand structure to function relationships that eventually lead us in designing, indeed, more durable or sustainable construction materials, cementitious materials in this specific case that I will present today. So this is the outline of my presentation. So after a brief introduction into the concrete difficult relation with the environment and cement chemistry, I will give you the details of the methods we use in the lab to tackle several questions that are connected with the cementitious materials. In the specific case, we look into cement hydration processes and also cement as a carbon sink. And in the last part of the presentation, I will cover recent results concerning the durability of ancient Roman concrete. So let's say that concrete is an outstanding material. It's strong, durable, and versatile construction material. And really, it's not only just strong, but it's and durable and versatile, but it's also extremely cheap. And we are here dealing with this material for all of these incredible characteristics that it has. So the unfortunate environmental impact of the material we know very well is not related to the fact that has a quite low embodied energy and embodied carbon footprint compared to other materials, but the problem stays in this graph of the production of this wonderful material, and it is accounting. But it is widely used in many applications, you will know very well, and these 4 billion metric tons per year of production then leads to a significant carbon footprint, which accounts to about 1% of the total US CO2 emissions, which is significant. So this then has to add to the challenge of our future that holds people moving from rural places to urban spaces, and the urban areas will definitely require this outstanding material to be used, and that definitely plays a significant challenge, considering that the CO2 emissions are keep rising, and we need to find a way to stabilize those and reduce them. So you will probably know very well that concrete is this composite material of aggregates, fine and coarse aggregates, and cement. The cement and cement is cement paste is at the current situation produced using a method that is quite old, and it includes calcining, clay and calcium carbonate at very high temperatures that account for significant energy and carbon footprint. And of course, because we use calcium carbonate as a precursor of clinker, eventually this leads to the decomposition of the molecule of calcium carbonate, limestone, into CO2 that you will see eventually never or maybe partially comes back into the system, but is accounting for 50% of the carbon footprint. So I just told you that CO2 doesn't come back because clinker, once introduced into the mortar or concrete system and water, eventually undergoes reactions that do not include CO2. And these are hydration processes that lead to ettringite, portlandite, and calcium silicate hydrate, CSH, that basically is the key component of ordinary Portland cement, and provides some sort of a glue. Here in this graph, you see this light blue CSH growing around the clinker particles and eventually connecting aggregates. And in the middle, you see actually a result from Raman imaging in my lab, where we monitored actually these reactions. And in white, you see clinker component alite, and in green belite that evolve over 24 hours. And you see the blue, the formation of CSH and Portland calcium hydroxide in red. So this is a kind of a topic of one part of this presentation, because this image is definitely shedding a light on processes that are quite difficult and complex to understand. When it comes to lowering cement and concrete environmental impact, we have been, of course, working actively in this field. We as a society and community, and here you see one can act on many different stages. On materials production stage, increasing energy efficiency, alternative use of alternative fuels, very frequent clinker replacement, maybe carbon sequestration and at the cement plant, and cement and aggregate production using captured carbon from the air. On the design and construction, use less by design and increase the lifespan, definitely would at the long run reduce the emissions. And of course, there is also stages of use and end of life that offer opportunities to reduce the carbon footprint of this material. Here in bold are strategies that are already widely implemented in the field, whereas standard font is strategies that are being researched and implemented at the lower level in the industry. So this is what is our vision here in Masic Lab, and the vision is definitely something that maintains the material in certain parameters that will satisfy constraints, industrial constraints, but definitely introduce other functionalities into the same material. And indeed, we believe that the potential of concrete, the green concrete, is in the multifunctionality. When I talk about multifunctionality, I'm talking about the ability of CO2 to regain that CO2 emitted into the atmosphere by mineralization processes that could involve both aggregate and cementitious cement paste, and therefore lead to lower carbon footprint. Also, biology is a great, offers a significant number of examples of high performance materials that actually are synthesized at room temperature and atmospheric pressure, which might allow us to, translate some of that knowledge into cementitious materials, but also biological materials and structures offer an incredible design space that might lead to might lead to solutions that require less material for the same performance, and use less by design. And one important component that is really overlooked in terms of cementitious materials and concrete, I think, is durability. We have wonderful examples in the ancient world that I will definitely present today. Some of these examples to you as well, that show intrinsic self-healing mechanisms and properties, self-healing mechanisms that lead to properties that overperform any of the modern concrete designs. And last but not least, there is a very active space now where we use cementitious materials as maybe energy storage or self-heating material by introducing small amounts of carbonaceous materials into the nanoporous network of cement, introducing a completely new, outstanding functionalities with the potential to, again, have energy storage made out of concrete, and perhaps sensing structures through this composite material. So let me now move into a method section and give you an idea of this time-space resolved chemical deconvolution of cementitious materials. And I like to start with saying why concrete is such a great material. It's versatile because of its workability. So you make any shape, you pour concrete in, and eventually it solidifies through hydration. This process is very well known and established. But interestingly, it's a very complex slurry that evolves, and we are still kind of struggling in understanding all the fundamental processes that that occur, for example, in this early stage of cement and concrete setting, so properties that are strictly related to workability. And I like to cite my colleague Henry Van Dam that really beautifully describes the need for more concrete knowledge about concrete chemistry. He says that concrete is a remarkably rich deposit of interesting and contemporary research questions, all contained in its ambiguities, granular or continuous, liquid or solid, crystalline or glassy, smooth or rough, porous, brittle or ductile, material or process. So really, we need to lay solid basis to understand from the fundamental standpoint this evolving material evolving over time. How do we actually can study these cementitious materials? And probably you came across many different techniques and tools to investigate, but what really essential for us is that we are able to access material from multiple scales, starting from nanoscopic level up to the macroscopic performance. We should be able to really capture multiple phases, including amorphous materials that are integral part of this changing mix. And that's the last point. Everything is evolving over time, and evolution is an essential parameter that eventually lead to changes in properties. And understanding this, to understand all this, we need techniques that have a high spatial resolution, high chemical sensitivity, and high temporal resolution. And trust me, it's a challenging set of requests here. And as I will try to show you in this presentation, Raman spectroscopy has all of these covered, and is an interesting opportunity for us to investigate the cementitious materials in bigger detail. So just for those that never heard about Raman spectroscopy, and I'll be not mad if you never heard about it, it's not a standard tool. This technique is basically using lasers to excite molecules. So it's a molecular level technique that after the laser hits the molecule or your sample, these molecules undergo an excitation to a virtual state that eventually is not stable, and the return to origin can occur through the elastic scattering. So the arrow is of the same length, but often occurs through return to the vibrational levels that actually lead to an inelastic scattering and a shift in the energy. These shifts we can detect using our detectors that eventually lead to peaks in our Raman spectrum. And these peaks will inform us on the short range environment of the molecule that was hit by the laser, which eventually opens incredible opportunities to sense and use fingerprints to sense many different aspects of the sample, including component concentration, mechanical and chemical environment, crystallinity, homogeneity, crystal orientation through polarization approach, and so on. And this slide shows a little bit of many things that my lab has tackled and studied in past decade or so. And most of these papers carry Raman spectroscopy as a key component to inform on biological or biomineralized materials, high performance materials. We have also cancer mineralization in breast cancer, a lot of biomineralization that can be nicely studied. And here on the right, you see what I will be covering today is cement hydration processes and ancient Roman concrete studies. So as I said, I would not be mad if you don't know about Raman spectroscopy, because Raman spectroscopy applied to cement chemistry started and stopped being used many years ago. You see, these are papers from 70s and 90s, where Raman spectroscopy definitely struggled from one of the biggest problems, that is the fluorescence, and with the advances in microscopy, Raman microscopy, especially confocal microscopy, we were able to overlook these, and we are talking about 2019 papers, and very recently, last year, we published this underwater confocal Raman microscopy study of real-world condition cement hydration. So the person behind this work is my former graduate student, Chad Law, and Chad basically was able to build under the microscope this nice cell that eventually allows your sample to be accessed by the microscopy objective, but at the same time sample is exposed to constant supply of water, making this condition here comparable to hydration of cement paste in the real world, and we would just put some oil on top just to prevent water from evaporating and do all these studies. And really what Raman is very good at is capture all of the phases that are in the sample, cement sample, and capture all the transformations that occur over time. So indeed, we just define a protocol that eventually does a four-dimensional data collection, and we have X, Y, Z, time, and wave number as dimensions. And because the efficiency of these instruments became extremely good, we are able to, for each sample, collect a 250,000 of spectra that then are processed simultaneously in a big data cube, and that really allows you then to apply a systematic statistical approach to all these data sets, and you can do many things because of the number of spectra, and for example, you can find the basis, can apply basis analysis that brings out a basis spectra and component maps, and this is what you get from one scan of cementitious material, and you see you have an alide and most of the other phases that are formed, and of course of extreme importance for cement hydration. Let me just give you a few insights in these results, and of course I invite you to read the paper and also contact me if you have any questions. So what we were able to do, for example, is analyze just the OH vibration region, where of course you can find peaks associated with calcium hydroxide and CSH, and by careful analysis of these 250,000 spectra for each sample, we were able to identify actually disordered calcium hydroxide as a component, and disorder is quantified through the evaluation of the peak position and the peak width. You will notice that the crystalline calcium hydroxide always, gives you a peak at 3614 and with a width of 8 more or less wave numbers. But then there is this phase that is shifted and broader with a peak hydroxide peak broader. Broadening means that the order is lacking in, so there is some disorder in the structure that can be easily analyzed and mapped. You see, we did it through the time series peak analysis, where we could monitor both width and position, and so this is the example of a data set over 24 hours. So here's the time, and you will notice that the peak slowly sharpens. This is peak width and shifts as hydration proceeds, and these are peaks associated with the hydroxide, calcium hydroxide portlandite. So I'm just thinking, okay, cool. So here you see there is a shift from disorder to crystalline, and also this is a shift in broadening, so it gets sharper, and shift in position that are correlated and clearly show a new phase, disordered calcium hydroxide appearing in the early stages of hydration. We are talking about first 6 hours. You can also eventually get clear understanding by fitting peaks associated with CSH in the OH region, and here we were able to confirm the defective terbermarite model, Gartner's model, that was published a few years ago with a clear indications of calcium and silicon hydroxide environments. So what is also cool about the approach is that we get images, and together with the colleague Franz Ulm, we were able to do correlation function, apply correlation function to these images, and eventually really get a clear idea of volume fraction, cluster size, and characteristic distance of these forming units in the sample, and that eventually allowed us to realize that the CH, so portlandite, crystallizes far from C3S clusters, while CSH crystallizes on C3S, means allied surface, and that's quite known, but still having it confirmed through this approach was really encouraging. And also we realized that setting occurs when the C3S, CSH, and CH form an interconnected network that eventually gave us this beautiful opportunity to draw the process, the mechanism of the early stages of hydration, where you see allied dissolving, and then calcium is moving actually into pores where it starts to crystallize into portlandite through a phase that is this disordered calcium hydroxide phase. This disordered calcium hydroxide phase could be also nanoparticles that are moving from allied into the pore space, nanoparticles that would lead to that broadening as well. What else? I just said that this interconnected network that is formed eventually confirms the percolation theory as a mechanism. Good. Longer observations are also possible, of course, require a little bit more of time and also effort, but still, here is the example of 28 days evolution of phases captured by Raman, where you nicely see the development of CSH and of course slow dissolution and disappearance of halide. You notice also that belite in green didn't do much in the first days, but after day 7, I think starts a little bit to disappear clearly, confirming lower reactivity of belite. What else I wanted to share with you? Yeah, these longer observations, of course, are quite important because we are aiming, to tackle post-setting and curing process. Here you see some details of this after 1 day comparison with 7 days. We had a nice reference grain here of calcium carbonate, calcite, that we used to then, make sure that we are always at the same spot. And you see there is a correspondence here. And this allowed us eventually to really capture, hydration process and formation of C3S, CSH around the C3S. So I just told you that we are able to capture calcite and therefore carbonates in our sample, and that's what we are doing right now. We are trying to monitor and look into the processes that are interesting when it comes to sequestration of CO2 through mineralization in cementitious materials, and have a cement as a carbon sink. Carbon capture in cement is definitely something extremely attractive, and it would be ideal, carbon sink if we are able, to introduce alkaline reactants into the paste and eventually have a CO2 from thin air mineralized into the cement. There are many companies. I'm quite sure that in the audience here, there are people that have been part or are part of some of these examples, and I really don't want to go much into detail here. Everything is public. This is definitely an exciting field. It's something that holds incredible promise, especially if you think about the aggregate. Aggregate occupies a lot of space in the concrete, and if we are able to have aggregates made out of anthropogenic carbonates in a sense of captured CO2, then this is extremely promising. Of course, carbon cure, for example, pumps directly CO2 into the hydrating mix, and this is what we try to repropose in our cell, where we basically use the C3S and some bicarbonate in the system, showing really encouraging results. Where if you look at this Raman image here, you see green, that is unreacted C3S, blue is a CSH, and calcium carbonate is in red. And do you see any kind of red here? Maybe a little bit here, but most of the sample is pink, meaning that actually CSH is colocalized with calcium carbonate. And this really nicely shows association between calcium carbonate and CSH that was actually observed some years ago, 20 years ago, even more, by, again, Henry Van Dam, where they used fine calcium carbonate particles as seeding agents for CSH formation. So this actually is definitely one of the most exciting directions and parts my lab is taking right now, and I'm truly looking forward to see more of this work unfolding in the lab using these tools. But of course, you will well know that calcium CO2 absorbed into concrete is not just staying there, and unfortunately, is changing the pH, and eventually, if that process goes down to rebar and steel, we observe degradation. And of course, it's now the balance of these processes that can be carefully and should be carefully tuned to use this kind of important opportunity, because if you look at this Nature Geoscience modeling paper, it really shows a quite significant uptake potential of concrete and cement over time. So, so we are definitely excited about this. Here I'm showing you another image of 3D printed concrete sample. 3D printing is, I already mentioned, is a great promise to use that strategy, apply the strategy, use less material but still maintaining the structural integrity of interest. And if you deposit material where you want, this opens an incredible design space that can be explored. And here is the Raman image of carbonated concrete sample. Here we are talking about large areas, so about a centimeter by quarter of centimeter area, so big chunk, and characterized till resolution of I think 1 micron in this image, and mapped all the phases that the Raman can be used for. Of course, there is a lot of calcite carbonate phases in this binder, and I think this could be the technique to go for when it comes to carbon sink studies. All right, so this is my last part that I will cover today, and about concrete's green potential, and it relates to our work on self-healing concrete and specifically ancient Roman concrete. And really, ancient Roman concrete is an outstanding material that requires less energy to produce, uses often recycled materials in the form of ground pottery and called cacio pesto. But most importantly, it is proven to last much longer compared to our solution. And of course, the key question for us is what are the origins of the extreme long-term durability of this material that is basically an interesting mix. So Romans used deposits of volcanic ash around the Pozzuoli near Naples, and introduced into the mix of sand aggregates and lime, which then basically opened the possibility for this mix to go through hydration processes and build a calcium aluminum silicate hydrate that is the equivalent of calcium silicate hydrated or ordinary Portland cement, and again create this glue between big and small aggregates. So currently we are trying to understand this complex material, and you will understand that it gets even more complicated because this material stayed there for 2,000 years, and understanding pozzolanic reactions and post-pozzolanic reactions is a great challenge. And there is a colleague of mine, Marie Jackson, that spent a lot of time looking into these materials and processes, and the assumption is that fluids supersaturated in the calcium, silicon, aluminum, sodium, and potassium crystallize into stratlingite or aluminum tobermarite in vesicles, or maybe gas bulbs or interfacial zones and pore spaces, and reinforce constantly through these processes the structure. So the questions that we asked in my lab are where the calcium comes from, and how the relic lime clasts that you will learn are the integral feature of Raman concrete are playing. Are they playing any role, and could they be the missing link in self-healing picture? So we studied some very prominent structures around Rome. This is an example of tomb of Caecilia Metella, concrete that dates back to 1st century before Common Era. And you see, this is how these samples look like under the microscope, and we analyzed basically the interface between volcanic small aggregates and the binder, and we're able to map chemical phases that indeed include aluminum tobermarite, stratlingite, but also we were able with Raman get the binding phase that eventually is calcium aluminum silicate hydrate at an interface here. So we then clearly managed to analyze systematically these interfacial zones, and we're able to show the constant evolving of these interfaces in a long-term remodeling of the structure, let's say aggregate binder interface, and that is extraordinary, because if you think about the standard Raman standard concrete, these interfaces are generally quite weak, if not even, let's say, quite stable over time, if not weakening because of the ASR and the other processes that occur. We also studied these ceramic aggregates, and also in this case, ceramic aggregate shows the reactivity that again shows the calcium silicate hydrate, but also other phases such as calcite and vaterite in the binding phase, showing that there is also carbonation process occurring, of course, over 2,000 years. Most importantly, what we observe in many of these samples is the evidence of post-pozzolanic processes that are filling the cracks and filling the pores. And what came out from this investigation that is mainly calcite. Here is a crack in the Raman concrete, and main component in this crack is calcium carbonate, calcite. And so that led us to analyze a very specific feature of Raman concrete, and this is a ubiquitous feature that are these white inclusions called relict lime clasts that you can find in every sample of Raman concrete, and they are meant to be there because of the poor mixing of the lime volcanic ash sand mix, and they would then stay there and without any function. And you see here is a optical microscopy of Raman concrete fracture surface, and you see these inclusions all over the sample. So we, of course, applied our tools to study some of these inclusions, and we came out with these results that show an important differentiation between calcium carbonate phases in the lime class, showing clearly that these lime clasts undergo or went through a process called hot mixing, where basically instead of using a slaked lime, so lime that is baked and then hydrated and then introduced into mix, but we believe that the Romans used partially or entirely quicklime in their mix. And quicklime, of course, leads to very special process of heating of the mix, and that's where the hot mixing comes from, and creates very specific conditions around these inclusions, and this low humidity conditions lead actually to polymorphs of calcium carbonate that are different from calcite that would be formed if the slaked lime was used. And that eventually led us to think that that hot mixing would systematically create actually these inclusions, because the water would not be there to dissolve lime, and the quick lime would be incorporated. And once incorporated, it would undergo some reactivity, but still would stay like white chunks of calcium-rich inclusions that eventually, if the crack comes out and goes through the lime clast, would serve as a source of calcium for the processes that are then healing processes. And indeed, around every lime clast, we would observe this red kind of phase that is more rich in calcium compared to yellow phases. And this is kind of an indication that these clasts actually played an important role in the phases around them over time. And indeed, this technology now, it's patented pending, and we have a startup that is working on the commercialization of these solutions. So I think my time is up, and I just want to conclude with this slide. Unfortunately, I had no time to talk more about 3D concrete printing and conductive cement, but this is definitely exciting avenue of work for multifunctional concrete. I do believe that there is a great future for concrete, and the future is multifunctional, and we can't wait to introduce new functionalities such as self-healing, carbon sink, or self-heating, or any other function that we could think of, and creating an infrastructure that would bring new spaces for use of this outstanding material. So with this, I would like to acknowledge my collaborators, and thank you for the attention. I'm happy to take questions.
Yeah, thanks so much for your presentation, Professor Masic. We've got one very laudatory comment here. The attendee wrote, groundbreaking work, Dr. Masic. Is the calcite observed in Raman imaging from cement? Ideally, the CSH ring should nucleate and grow around calcite particles too, which is not seen here.
Yeah, correct. It's just early stage. We are doing longer time scales that should confirm nucleation as a mechanism. Yeah.
Another attendee asked. He commented on the volumes of CH and some of the Raman figures are high based on a quick visual. Do these quantities match typical paste values?
Yeah. Eventually, it stabilizes. I mean, it saturates to the standard volumes that eventually remain of Portlandite there. Yeah. I mean, of course, it's a heterogeneous process, determined by porosity and other aspects. But statistically, yeah, these of course would eventually converge.
And a further question is about unreacted CaO. So if reacts, does it cause volumetric expansion? Well, let me restart. Sorry, unreacted CaO, if reacts, causes volumetric expansion and cracking. Maybe the cracks were formed by this expansion and later filled the crack space and carbonated.
Mm. Yeah, not really. It does expand. This is in terms of translating this technology is an important question. You don't want your material um, to have cracks due to the expansion. So you definitely tune carefully the composition and amount. But what we showed through self-healing processes and investigation is that the real crack heals and stops water from flowing. So.
And one further question actually might be directed more at the team here at CS Hub, but it's on the nature of the optimal use of concrete and it's optimizing its life cycle emissions. So maybe Randy, you could touch on that a little bit.
Sure. I think I think the individual was maybe reacting to a comment that less is not always the more sustainable. That there are cases where it's important for the structure durability may be more important, stiffness may be important because of the fact that they provide use phase benefits. But I think that the gist of the comment is that there are a lot of opportunities to find ways to deliver the same amount of performance that we get today with either less materials or materials that are more, carbon friendly, if you will. And, like this comment about self-healing as an example where you are going to get sustainable performance by not having to replace that or not having to repair that. Right. And so it's a very complicated space for sure, but there's a lot of, as we saw today, a lot of opportunities to look at some new directions here.
Yeah, if I may stress this self-healing aspect, I think it is really cool to have a self-healing material. That current self-healing, solutions are definitely expensive. So if you can come up with a cheap self-healing, material, eventually it allows you to play with credits maybe and further reduce the carbon footprint of your material.
So we had two further comments about carbonation. So one attendee was asking about how much CO2 released into the atmosphere through the cement production process is actually reabsorbed, is currently being reabsorbed, and then further, what are the rates of absorption in some of these ancient lime, pozzolan concrete mixtures you're looking at?
That's a great question. I mean, the models show significant amount reabsorbed, like old concrete, perhaps 25% might be reabsorbed. So 50% of the CO2 associated with lime, with the calcium carbonate limestone. So quite promising. Of course, the second follow-up question is the holy grail. When it comes back, how long it takes, and what are the final properties? And of course, this is where we want to go. We need to push fundamental understanding of CO2 interacting, mineralizing, and cementitious material, with then estimating and quantifying all these parameters.
One further question we have here is there any research on how alginate-rich seaweed may improve self-healing as well as CO2 reduction in concrete?
Not that I have done anything. I worked marginally on nanocellulose, which showed quite interesting properties in terms of mechanical performance, especially in tension. But no, not from my side.
And then one other question we have here is how might the fly ash that's used today compare to the Roman volcanic ash that was used in ancient mixtures?
I think they are equivalent. I mean, some more active than others, but they are definitely equivalent. So they will do the job.
And I guess following on that, so given the reduced availability of fly ash, how do you see a replacement appearing in the next few years?
Oh yeah, so replacement is so what our self-healing work of Raman concrete stresses is the point that it's not just volcanic part that is playing the role. Is the calcium source that is essential to create calcium aluminum signature hydrate, and we don't know. we know, we are trying to understand, you know, all these processes, but what we are saying is that there is a calcium carbonate component that plays an essential role.
All right, and that is the end of our questions here. So thank you very much, Professor Masic, for your presentation and for going into depth here, answering all the questions. We really appreciate all your contributions. And additionally, thank you all to have attended. We really appreciate your ongoing attendance here at our webinar series. It's a pleasure to bring speakers to you to share their work. And we'll be following up with this presentation with a recording, and you'll be able to see that in the coming days, and we'll all keep you posted on the webinar series we have here. And thank you very much, and we hope you have a very good day.
Thank you all for listening. Bye-bye.